Tonight, we're going to explore something that should keep you awake, but might instead ease you into the most peaceful sleep you've had in weeks. We're going to ask a question that humans have whispered to themselves since the first night someone looked up at the stars and wondered, where does everything end? Settle in. Let the weight of the day drift away. Whether you're listening in the quiet hours before dawn or in those peaceful moments before sleep, you're in the right place. Because tonight, we're traveling to the edge of everything, to the boundary of existence itself, if such a boundary even exists. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive and reminds me that these quiet stories still find their way to gentle hearts, like yours. Your presence here matters more than you know. Now, let's begin with something you already understand deeply, something written into your very bones. Every object you've ever encountered has a boundary. Think about it. Your skin separates you from the air around you. The walls of the room you're in right now mark where inside becomes outside. An ocean has shores, a box has sides, a country has borders. Even Earth itself has a surface, a clear line between planet and space. This understanding is fundamental to how we navigate reality. We are boundary-dwelling creatures. We spend our lives moving from one enclosed space to another, from bedroom to kitchen, from home to office, from city to city. We draw lines on maps, we build fences. The very concept of here only makes sense because there's a there on the other side of some dividing line. So when we turn our attention to the cosmos itself, to the totality of everything that exists, it feels only natural to ask, where is the cosmic wall? Where is the ultimate boundary, the final shore, the edge beyond which there is simply nothing? This isn't a modern question. It's ancient, primal. You can imagine it, someone lying on their back 50,000 years ago, watching the stars wheel overhead, suddenly struck by the thought, does this go on forever? Or is there an end somewhere out there? The question is so natural because it emerges from the deepest patterns of our experience. We live in a world of containers. The sky itself appears as a dome overhead. The horizon creates a circle around us. Everything we know is finite, bounded, contained within something else. But here's what makes this question so profound. The universe is not an object. It's not a thing sitting inside something else. The universe is everything. It's the stage on which all objects exist, the arena of reality itself. And that means our intuitions about boundaries honed over millions of years of evolution might not apply. When you ask, where does the universe end? You're not asking where a particular object stops. You're asking about the nature of existence itself. You're asking whether reality has limits. You're asking if somewhere eventually becomes nowhere. The answer is stranger than ancient people could have imagined. The universe might be infinite, stretching on forever with no edge at all. Or it might be finite but unbounded, curved back on itself so you could travel forever and never reach a wall. Or it might have edges we can never reach, boundaries defined not by space but by time, by physics, by the structure of reality itself. We don't know which is true, not for certain, but we know far more than our ancestors did. We've measured the cosmos. We've traced its history back 13.8 billion years. We've discovered it's expanding, carrying galaxies apart like raisins in rising bread. And in doing so, we've discovered something remarkable. The question, where does the universe end, transforms into a dozen equally fascinating questions. Where does the observable universe end? Where does space-time end? Where does physics break down? Each has a different answer. Each reveals a different kind of boundary. Together, they paint a picture far more subtle than a simple box with walls. 3,000 years ago, if you'd asked a Babylonian priest where the universe ended, he would have given you a confident answer. At the firmament, the great dome arching over Earth, separating the world of humans from the waters of chaos above. This wasn't poetry. This was their literal understanding of reality's structure, and from their perspective, it made perfect sense. Look up at the sky. It appears as a dome, doesn't it? The stars seem fixed to a surface overhead, rotating together. The sun and moon trace paths across this dome. Rain falls from above, as if water seeps through from some reservoir beyond. The blue of daytime sky suggests an ocean overhead, held back by an invisible barrier. The Babylonian model explained it all. Earth was a flat disk floating on a cosmic ocean. Above stretched a solid dome, the firmament, holding back the waters of chaos. The stars were holes punched in this dome or lights affixed to it. The sun and moon were divine beings traversing prescribed paths. It was tidy. Everything had its place. The universe was comprehensible, bounded, organized. The edge was visible overhead every day. You could point to it. The dome was the boundary between creation and chaos, between order and the formless void. Then came the ancient Greeks, and everything got more sophisticated. Around 350 BCE, Aristotle constructed a model that would dominate Western thought for nearly 2,000 years. Earth sat motionless at the center, not because humans were special, but because Earth was made of heavy elements that naturally sought the center. Around it nested crystalline spheres, each transparent and perfect. The moon occupied the innermost sphere. Then Mercury, Venus, the Sun, Mars, Jupiter, Saturn, each embedded in its own sphere, each rotating at its own rate. Beyond Saturn was the sphere of fixed stars, the outermost boundary of the physical cosmos. And beyond that, Aristotle was clear. Nothing. Not empty space, not void. Literally no existence of any kind. The concept of beyond simply didn't apply because there was no there for anything to be beyond. The outermost sphere wasn't a wall separating inside from outside. It was the absolute limit of reality itself. This was sophisticated thinking. Aristotle understood you can't have space beyond space. You can't have a place outside the universe. The universe, by definition, is everything. If there was something beyond it, that would be part of the universe too. In the 2nd century AD, Ptolemy refined this model, adding epicycles, small circles upon circles, to match observed planetary motions. His system could predict positions with impressive accuracy. It could create calendars, guide navigation, explain eclipses. By medieval times, this Ptolemaic system had intertwined with Christian theology, the crystalline spheres populated with angels, the outermost sphere becoming God's dwelling place. The cosmos had become small, comprehensible, deeply meaningful. Earth at the center. The heavens arranged in perfect spheres. God beyond it all. The universe had an edge, and that edge was as theological as it was physical. It was beautiful. It was coherent. It was wrong. But before we could discover that, someone had to ask the right question. Imagine you're a Greek philosopher in the 4th century BCE. You've been taught the universe consists of nested crystalline spheres, with the sphere of fixed stars marking the absolute boundary. Beyond that, nothing. Not empty space, but the complete absence of existence itself. You're curious. You like testing ideas by pushing them to their limits. So you perform a thought experiment. Imagine you could travel to the edge, to that outermost sphere. You stand on its inner surface. Now you stick your hand out. You reach toward the edge, toward where existence is supposed to end. What happens? If your hand passes through, then clearly there must be space beyond. The edge wasn't really the edge. There's something on the other side, even if just empty space. The universe must be larger than you thought. But if something blocks your hand, if there's a barrier, then that barrier exists. It's made of something. And if it exists, it's part of the universe. Which means the supposed edge wasn't the edge. It was just another object within a larger space. This is Archytas's paradox, named after Archytas of Tarentum, a philosopher who lived around 400 BCE. And it's devastating to any model that tries to place a simple boundary at the edge of space. If there's a wall, you can ask what's on the other side. If there's no wall, you can keep going. Either way, the universe extends beyond where you thought it ended. The paradox reveals something profound. Space is not an object that can have an edge like a table has edges. Space is the arena in which objects exist. It's the stage, not a prop on the stage. And stages don't have edges the way props do. Medieval scholars proposed various solutions. Some said beyond the stars lay the infinite presence of God. Not a place, but divine essence transcending physical space. Others suggested asking what's beyond the universe is like asking what's north of the North Pole. A category error, a question that seems grammatical but makes no sense. But these solutions remained speculative. For thousands of years, humanity lacked tools to investigate the cosmos's actual structure. We could argue philosophically whether the universe had an edge, but we couldn't measure it. We couldn't test our ideas against reality. That began changing in 1610, when Galileo turned a telescope toward the night sky. What he saw shattered the crystalline spheres forever. The moon had mountains and craters. It was a world, not a perfect sphere. Jupiter had 4 moons, proving not everything orbited Earth. Most profoundly, when Galileo looked at the Milky Way, he didn't see glowing cloud. He saw stars, countless individual stars, too faint for naked eyes but perfectly clear through his telescope. The universe was suddenly larger than anyone imagined. Those weren't holes in a dome. They were distant suns scattered through vast space. The old boundaries were gone. The crystalline spheres were fiction, but new questions arose. How large was this universe? Were stars scattered infinitely? Or was there still some boundary just farther away? To answer those questions, humanity would need to measure the cosmos. We would need to build a ladder of techniques, each extending our reach farther, each teaching us something new. The edge, if it existed, was about to recede much farther than anyone had conceived. To find the edge of the universe, we first had to learn how to measure it. And that journey began with a problem that tormented astronomers for centuries. The stars appeared as mere points of light, offering no clue about their distance. Were they nearby lanterns or distant suns? The breakthrough came from a simple geometric principle: parallax. Hold your finger at arm's length and look at it with one eye, then the other. Your finger appears to shift position against the background. That shift tells you how far away your finger is. The same principle works for stars, but the challenge was finding a baseline large enough to measure their incredibly vast distances. For thousands of years, astronomers knew the principle. As Earth orbits the Sun, our viewing position changes by about 186 million miles over 6 months. If a star is close enough, it should appear to shift position slightly against more distant stars. Measure that shift, apply geometry, and you can calculate the distance. The problem was that the shifts were vanishingly small. Even the nearest stars show parallax of less than 1 arcsecond. That's 1/3600th of a degree. Imagine dividing a single degree into 3,600 slices. That's the precision required. Astronomers tried for centuries. They built increasingly sophisticated instruments. They developed better techniques for measuring stellar positions. But the stars stubbornly refused to reveal their parallax. Some began to wonder if Earth wasn't moving at all. Then, in 1838, a German astronomer named Friedrich Bessel achieved what had eluded astronomers for 2,000 years. Using a heliometer, an instrument designed to measure small angles with unprecedented precision, Bessel detected the parallax of a star called 61 Cygni. The parallax was tiny, 0.314 arcseconds, but it was real, measurable, repeatable. From that measurement, Bessel calculated that 61 Cygni was about 11 light-years away, roughly 65 trillion miles. This was staggering. The distance to the Sun, 93 million miles, had been humanity's measure of cosmic scale. Now, Bessel had proven that even nearby stars were thousands of times farther away. The universe had suddenly become incomprehensibly larger. Within a year, 2 other astronomers independently measured parallax for other stars. Thomas Henderson measured Alpha Centauri at 4.3 light-years. Friedrich Struve measured Vega at 25 light-years. The parallax method worked, but there was a limit. Parallax only works for relatively nearby stars. Beyond a few thousand light-years, the shifts become too small to measure. The European Space Agency's Gaia satellite, launched in 2013, has measured parallax for over 1 billion stars with unprecedented precision. But even Gaia can only reach about 30,000 light-years. Our galaxy is 100,000 light-years across. Andromeda is 2.5 million light-years away. The observable universe extends 46 billion light-years in every direction. Parallax gave us the first rung of the cosmic distance ladder, but we needed other methods to reach farther. We needed objects whose true brightness we could determine, objects bright enough to see across millions or billions of light-years. We needed what astronomers call standard candles. Henrietta Swan Leavitt never set out to revolutionize cosmology. In the early 1900s, she worked at Harvard College Observatory as one of dozens of women hired to analyze astronomical photographs, work considered too tedious for male astronomers. These women, called computers, measured stellar brightness from photographic plates, cataloging the heavens one star at a time. Leavitt's assignment was to study variable stars in the small Magellanic Cloud, a dwarf galaxy visible from the southern hemisphere. Night after night, she examined plates, noting which stars had brightened or dimmed, measuring their periods of variation. And then she noticed something remarkable. The brighter a Cepheid variable star appeared, the longer its pulsation period. A Cepheid that took 10 days to complete one cycle was intrinsically brighter than one that took 5 days. This relationship was precise, consistent, mathematical. Here's why this mattered. All the Cepheids in the small Magellanic Cloud are roughly the same distance from Earth, so differences in their apparent brightness reflect differences in their true brightness. By plotting periods against brightness, Leavitt had discovered a relationship between period and luminosity. This was revolutionary. Measure a Cepheid's period. Easy, just watch it brighten and dim, and you immediately knew its true brightness. Compare that to how bright it appears from Earth, and you could calculate its distance. It's like seeing a light bulb in the distance. If you know it's a 100-watt bulb, you can estimate how far away it is by how bright it looks. Leavitt published her discovery in 1912. A few astronomers recognized the significance immediately. This was a cosmic measuring stick, a way to determine distances far beyond the reach of parallax. Enter Edwin Hubble. In the 1920s, working at Mount Wilson Observatory with the 100-inch Hooker telescope, Hubble turned his attention to spiral nebulae, fuzzy patches some astronomers thought were gas clouds within our galaxy. Using Leavitt's period luminosity relationship, Hubble identified Cepheid variables in the Andromeda Nebula. He measured their periods, calculated their distances, and arrived at a stunning conclusion. Andromeda was about 900,000 light-years away. We now know it's actually 2.5 million light-years, but his fundamental conclusion was correct. This distance placed Andromeda far beyond the Milky Way. It couldn't be a gas cloud within our galaxy. It was a galaxy itself, an island universe containing hundreds of billions of stars. Hubble announced his results in 1924. The universe had transformed overnight from a single galaxy to a cosmos filled with countless galaxies scattered across millions of light years. Cepheids extended our reach dramatically, allowing us to map nearby galaxies. But most galaxies lie billions of light years away, far beyond where even the brightest Cepheids can be resolved. To reach those distances, we needed an even brighter standard candle. We needed exploding stars. Not all supernovae are created equal. When a massive star's core collapses, the resulting explosion can vary dramatically in brightness. These aren't reliable standard candles. But there's another type called type Ia that occurs differently, and these explosions are remarkably consistent. A type Ia supernova begins with a white dwarf, the remnant core of a dead star, about Earth-size but containing roughly the Sun's mass. If this white dwarf is in a binary system, it can pull matter from its companion. As material accumulates, its mass gradually increases. There's a limit, though. When a white dwarf reaches about 1.4 times the Sun's mass, the Chandrasekhar limit, it becomes unstable. The pressure triggers runaway nuclear fusion. The entire white dwarf explodes in a thermonuclear detonation, releasing as much energy in weeks as the Sun will emit in its entire 10 billion year lifetime. Here's the crucial point, because type Ia supernovae always occur when a white dwarf reaches the same critical mass. They always release roughly the same energy. They all reach approximately the same peak brightness. They're cosmic lighthouses, standardized beacons visible across billions of light years. This makes them perfect for measuring vast distances. Find a type Ia supernova in a distant galaxy, measure how bright it appears, and you can calculate how far away it is. In the 1990s, two independent teams began using type Ia supernovae to map the universe's expansion history. They were trying to determine whether expansion was slowing down due to gravity, and if so, by how much. What they discovered shocked the scientific community. The distant supernovae were dimmer than expected, about 25%, fainter than they should be if the expansion were constant or slowing. This could mean only one thing. The universe's expansion isn't slowing down. It's speeding up. Something is pushing space apart, causing galaxies to accelerate away from each other. This mysterious force became known as dark energy. We still don't know what it is. It doesn't interact with light or matter in any way we can detect directly, but it makes up about 68% of the universe's total energy content. This discovery earned the team leaders the Nobel Prize in Physics in 2011, and it fundamentally changed our understanding of the universe's future and its boundaries. Type Ia supernovae can be seen halfway across the observable universe. Combined with parallax and Cepheids, they allow us to measure distances from nearby stars to the most remote galaxies, spanning from a few light years to billions of light years. And with that capability, we can finally begin to map the observable universe itself, to understand what we can see. how far it extends and what lies at the edge of our cosmic horizon. The ladder is built. The measurements are made. Now we can ask, what exactly are we measuring? What is this observable universe, and how does it relate to the universe as a whole? We've built our cosmic ladder. We can measure distances from nearby stars to the most remote galaxies. And now we arrive at the first real boundary, the edge of the observable universe. This isn't the edge of the universe itself. It's the edge of what we can see. Understanding the difference between the observable universe and the whole universe is crucial to understanding whether reality has boundaries at all. The observable universe is the region of space from which light has had time to reach us since the Big Bang. It's defined not by where things are now, but by whether their light could have reached Earth. Light travels at 186,000 miles per second, roughly 300,000 kilometers per second. Nothing moves through space faster. This creates a fundamental limit on what we can observe. The universe is approximately 13.8 billion years old. You might think we can see 13.8 billion light years in every direction. But the actual radius of the observable universe is about 46.5 billion light years. How is this possible? The answer lies in the expansion of space itself. When light left a distant galaxy 13 billion years ago, that galaxy was much closer, perhaps only a few billion light years away. But while that light traveled toward us, space was expanding. The galaxy was carried farther away by the expansion, even as its light journeyed toward Earth. By the time that ancient light reaches us today, the galaxy that emitted it is now about 46 billion light years away. Think of an ant walking across a rubber band toward you while you stretch the rubber band. The ant moves forward relative to the rubber, but the rubber itself stretches, carrying the ant's starting point farther away. By the time the ant reaches you, its starting point is much farther than when it began. Light from distant galaxies works the same way. Photons travel toward us at light speed, but space between us and the source expands, carrying the source farther away. This creates a sphere around Earth with a radius of 46.5 billion light years. Everything within this sphere is potentially observable. Everything beyond is fundamentally unobservable. The light hasn't had time to reach us yet. This boundary is called the cosmic light horizon, or particle horizon. It's the limit of what we can possibly see. But here's what's crucial. This boundary is not a physical edge. There's no wall, no barrier, no place where space stops. The observable universe isn't a bubble sitting in void. It's simply the limit of our view. Imagine standing in dense fog. You can see clearly for maybe 100 feet in every direction. Beyond that, fog obscures everything. That 100-foot circle is your observable area. But the world doesn't end at the edge of your vision. There's more fog, more ground, more world beyond what you can see. The observable universe works the same way. The boundary is in our perception, not in reality. Imagine you're on a ship in the middle of a vast ocean on a foggy day. You can see the water clearly for about a mile in every direction. Beyond that mile, fog becomes too thick. Your visible ocean is a circle, 2 miles across, centered on you. Now imagine your friend is on another ship 10 miles away. They have their own circle of visibility, also about a mile in radius. Some of what they see overlaps with what you see, but they also see regions beyond your fog horizon, areas you cannot see. Are you at the center of the ocean? No. You're both just standing at points in a much larger ocean, each with your own limited circle of visibility. The fog creates a horizon that appears centered on you because you're the observer. The horizon moves with you. It's not a feature of the ocean, it's a feature of how far you can see. The observable universe is exactly like this. From Earth, we can see about 46.5 billion light-years in every direction. That creates an observable sphere centered on us. But we're not at the center of the universe. There is no center. If intelligent beings exist in a galaxy 40 billion light-years from Earth, they have their own observable universe, a sphere extending 46.5 billion light-years from their location. Some of what they see overlaps with what we see, but they also see billions of galaxies we can never observe, galaxies beyond our horizon but within theirs. And we see galaxies they cannot observe. Neither civilization is more central. We're both standing at different points in a much larger universe, each with our own limited view. The observable universe isn't a thing. It's a description of what one particular observer can see from one particular location at one particular time. Move to a different location, and the boundary moves with you. You're always at the center of your own observable universe, just as everyone else is at the center of theirs. If you could instantly teleport to a galaxy at the edge of our observable universe, 46 billion light-years away, you wouldn't find a wall. You'd find yourself in the middle of space, surrounded by galaxies with your own new observable horizon extending 46.5 billion light-years from your new location. The edge of the observable universe isn't a place you can travel to. It's not a destination. It's the limit of how far light can have traveled to reach us since the beginning of time. And this raises the question, what lies beyond that horizon? When astronomers map the observable universe, they find something remarkable. It looks essentially the same in every direction. This property is called isotropy. Point a telescope north and count galaxies. Then point it south, east, west, any direction, and you see the same thing. The same density of galaxies. The same types of structures. The universe has no preferred direction. This has been measured carefully. Astronomers have divided the sky into millions of patches and counted galaxies in each. The result is clear. The universe is isotropic to high precision. Some patches have slightly more galaxies, some slightly fewer, but these variations are small and follow statistical patterns. On average, the universe looks the same in all directions. Isotropy alone could be consistent with Earth being in a special location. Maybe we're at the center of a sphere. But there's no reason to think Earth is special. We're not at the center of the solar system. We're not at the center of the galaxy. There's no indication our galaxy is at the center of anything. This leads to the cosmological principle. The universe is both isotropic and homogeneous. It looks the same in all directions from any location, and it has the same properties at every location. Put simply, the universe is pretty much the same everywhere when you average over large enough scales. If the cosmological principle is true, and all evidence suggests it is, then what we observe from Earth is representative of the whole universe. The observable universe is a fair sample. This means that beyond our horizon, there are simply more galaxies, more stars, more planets, just more of the same, extending outward. How far? We can't answer with certainty. The observable universe contains about 2 trillion galaxies, each with hundreds of billions of stars. That's approximately 200 billion trillion stars in the observable universe alone. If the universe extends beyond what we can see, the total number is larger, possibly much larger. If the universe is infinite, then the number of galaxies is literally infinite. Infinitely many stars, infinitely many planets, infinitely many worlds scattered across endless space. We can't see them all. We're limited by our horizon, by how far light has had time to travel. But the cosmological principle tells us they're out there beyond the fog of distance and time. The observable universe is just our local patch. Beyond it stretches something larger, possibly infinitely larger, that we can only infer from the principles of symmetry and the evidence that space is uniform. But to know whether the universe is truly infinite or merely very large, we need to understand something more fundamental: the geometry of space itself. Does space curve back on itself like the surface of a sphere? Does it extend forever like an infinite plane? Or does it curve outward like a saddle? The answer determines everything. If space curves back on itself, the universe is finite but has no edge. You could travel in a straight line forever and eventually return to your starting point. If space is flat or curves like a saddle, it likely extends infinitely with no boundary at all. To answer this question, we need to look at the oldest light in the universe. Light from just 380,000 years after the Big Bang, when the cosmos first became transparent. We need to examine the subtle patterns in that ancient radiation, the cosmic microwave background, and measure how much space curves. The geometry of space holds the key to understanding whether the universe has an edge. To understand whether the universe has an edge, we need to ask a deeper question. What is the shape of space itself? Not the shape of objects in space, but the shape of the arena, the stage, the fabric of reality itself. This might sound abstract, even meaningless. How can space have a shape? Space is just emptiness, isn't it? The absence of things? But Einstein showed us otherwise. Space isn't nothing. It's something, a flexible, dynamic entity that can bend, stretch, and curve. And the way it curves determines whether the universe is finite or infinite, whether it has boundaries or extends forever. Before Einstein, space and time were thought to be separate, absolute, unchanging. Space was like an infinite grid extending in all directions, a fixed stage on which events occurred. Time was a universal clock, ticking at the same rate everywhere, flowing uniformly from past to future. Newton's physics assumed this framework. Objects moved through space according to forces acting on them. Gravity was a force that pulled masses toward each other across empty space, instantaneously affecting distant objects. But there was a problem with Newton's gravity. It acted instantaneously. If the sun suddenly vanished, Earth would immediately fly off in a straight line. The gravitational influence traveled infinitely fast, which seemed to violate the principle that nothing could travel faster than light. Einstein spent years wrestling with this problem. And in 1915, he published his general theory of relativity, which completely revolutionized our understanding of gravity, space, and time. Einstein's key insight was that space and time aren't separate entities. They're woven together into a four-dimensional fabric called space-time. 3 dimensions of space, length, width, height, plus 1 dimension of time, all unified into a single geometric structure. And here's the revolutionary part. This fabric can curve. Mass and energy don't pull on each other across empty space. Instead, they warp the space-time around them. A massive object like the sun creates a depression in space-time, like a bowling ball placed on a stretched rubber sheet. Other objects moving through this warped space-time follow curved paths, which we perceive as gravity. Earth isn't being pulled toward the sun by some mysterious force acting across 93 million miles of void. Earth is following the straightest possible path through space-time that's been curved by the sun's mass. We orbit because we're following the geometry of warped space-time. This isn't just a mathematical trick or a new way of describing the same old physics. Einstein's theory makes different predictions than Newton's, and those predictions have been tested extensively. When light from distant stars passes near the sun during a solar eclipse, it bends, not because the sun is pulling on the light, but because the light is following curved space-time. This was first observed in 1919 and made Einstein world famous overnight. Gravitational time dilation, the slowing of time in strong gravitational fields, has been measured with atomic clocks. GPS satellites have to account for general relativity, or their navigation would be off by miles. Gravitational waves, ripples in space-time caused by accelerating masses, were detected in 2015, a century after Einstein predicted them. General relativity isn't speculation. It's tested, confirmed physics. And it tells us that space-time is a real, physical entity that can bend and flex. Now here's where this becomes crucial for understanding the universe's boundaries. If space-time can curve locally around stars and planets, can it curve globally? Can the entire universe have a curved geometry? The answer is yes. And the type of curvature determines whether the universe is finite or infinite, whether it has edges or extends forever. Einstein's field equations, the mathematical heart of general relativity, relate the curvature of space-time to the distribution of matter and energy within it. The more mass and energy you have, the more space-time curves. And when you apply these equations to the universe as a whole, you get different possible geometries depending on how much total matter and energy the universe contains. There are three possibilities, three different shapes space can have on cosmic scales. Each leads to a profoundly different answer to the question, where does the universe end? Imagine you're a two-dimensional being living on a surface. You have no concept of up or down, only forward, backward, left, and right. You can move across your surface, but you can't perceive a third dimension. Now imagine three different surfaces you might live on. First, imagine living on the surface of a sphere, like a beach ball, or the Earth. If you start walking in one direction and keep going perfectly straight, you'll eventually return to your starting point. You've circumnavigated your world. The surface is finite, it has a definite total area, but it has no edge. You never reach a boundary or fall off. You can travel forever without encountering a wall. This is called positive curvature or spherical geometry. Parallel lines that start out parallel eventually converge and meet. The angles of a triangle add up to more than 180 degrees. Second, imagine living on an infinite flat plane, like an endless sheet of paper extending forever in all directions. If you walk in one direction, you never return to where you started. You just keep going forever. The surface is infinite. It has no edge, no boundary, no center. Parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. This is called flat or Euclidean geometry. It's the geometry you learned in school, the geometry that feels intuitively correct because it matches our everyday experience on small scales. Third, imagine living on a saddle-shaped surface that curves away from itself in all directions. This geometry is harder to visualize, but imagine a Pringle chip or a mountain pass. Curves up in one direction and down in another. If you live on an infinite saddle surface and walk in one direction, you never return. The surface extends infinitely. Parallel lines that start out parallel diverge, getting farther apart. The angles of a triangle add up to less than 180 degrees. This is called negative curvature or hyperbolic geometry. These three geometries, spherical, flat, and hyperbolic, represent the three possible large-scale shapes of space in our universe. If our universe has positive curvature, it's like the surface of a sphere, but in 3 dimensions instead of 2. It would be finite in total volume, but have no boundary or edge. If you traveled in one direction long enough, billions upon billions of years, you'd eventually return to your starting point from the opposite direction, having circumnavigated the entire universe. If our universe is flat, it extends infinitely in all directions. There's no edge, no boundary, no center. Space just goes on forever, with more galaxies scattered through endless void. If our universe has negative curvature, it also extends infinitely. The geometry is slightly different from the flat case. Distances and angles work differently, but the key point is the same. No edge, no boundary, infinite extent. So 2 of the 3 possibilities, flat and hyperbolic, lead to an infinite universe. Only the spherical geometry gives us a finite universe. Which one describes our actual universe? For most of the 20th century, we didn't know. Different measurements gave different results, all with large uncertainties. Some suggested slight positive curvature. Others suggested flat. The differences were within the margin of error. Then, in 2013, the Planck satellite completed the most detailed map of the cosmic microwave background ever made, and it gave us an answer. The cosmic microwave background is the oldest light in the universe. It comes from about 380,000 years after the Big Bang, when the universe first became transparent to light. Before this moment, the universe was filled with hot plasma, a sea of free electrons and nuclei so dense that photons couldn't travel far without scattering. The universe was opaque, like being inside a glowing cloud. But as the universe expanded and cooled, electrons and nuclei combined to form neutral atoms. Suddenly, photons could travel freely. The universe became transparent. Light that was trapped in the plasma was released, streaming through space in all directions. That light has been traveling ever since. Over 13.7 billion years of cosmic expansion, it's been stretched from visible wavelengths into the microwave part of the spectrum. Today, it appears as a faint glow coming from every direction in the sky, with a temperature of about 2.7 degrees above absolute zero. This cosmic microwave background isn't perfectly uniform. It has tiny temperature variations, hot and cold, spots, typically differing by only about 1 part in 100,000. These variations represent tiny density differences in the early universe, the seeds that would eventually grow into galaxies and clusters. But here's what matters for understanding the universe's geometry. The size of these hot and cold spots depends on the curvature of space. Imagine drawing a circle on a sphere, a flat plane, and a saddle surface. On a sphere, the circle appears larger than it would on a flat plane. On a saddle, it appears smaller. The curvature distorts the apparent size of objects. The same is true for the hot and cold spots in the cosmic microwave background. If space curves like a sphere, the spots should appear larger than they would in flat space. If space curves like a saddle, they should appear smaller. By measuring the angular size of these temperature variations with extraordinary precision, scientists can determine the curvature of space. The Planck satellite, launched in 2009 and operational until 2013, mapped the cosmic microwave background with unprecedented detail. It measured the temperature of the sky at millions of points, creating the most precise picture of the early universe ever obtained. The result? The universe is flat to within about 0.4% margin of error. Either the universe has exactly zero curvature, perfectly flat, or any curvature is so slight we can't detect it with current measurements. This is a profound result. It means that to the best of our ability to measure, space has Euclidean geometry on the largest scales. parallel lines stay parallel. The angles of cosmic triangles add up to 180 degrees, and crucially, this strongly suggests the universe is infinite. A flat universe has no natural boundary. It extends infinitely in all directions. There's no edge, no wall, no place where space stops. The observable universe, our 93 billion light-year sphere, is just a tiny patch of an infinite whole. Now there's a caveat. The measurements show the universe is flat within the observable region. It's possible that the universe has very slight positive curvature, so gentle that it only becomes noticeable over distances much larger than we can see. Imagine measuring the curvature of Earth by examining a 10-foot patch of ground. You'd conclude it's perfectly flat, because you can't detect the gentle curve. If the universe has a very large but finite size, say trillions of light years across, we might not be able to detect the curvature from our limited vantage point. So we can't be absolutely certain the universe is infinite. But the simplest interpretation of the data is that the universe is indeed flat and therefore infinite. And if that's true, then the universe has no edge in space. It goes on forever, filled with galaxies and stars and worlds beyond counting, stretching endlessly in all directions. Yet there's another kind of boundary we haven't discussed yet. Not an edge in space, but an edge in causality, a horizon beyond, which we can never reach no matter how long we travel or how fast we go. We've established that space is likely flat and infinite, extending forever with no edge. But there's a different kind of boundary we need to discuss. Not a wall in space, but a wall created by the expansion of space itself. This boundary doesn't sit at some fixed distance waiting for you to reach it. It's more insidious than that. It's a horizon that retreats from you, a destination that moves away faster than you can approach it, no matter how fast you travel. This is the cosmic event horizon, created by the accelerating expansion of the universe, and it represents a true, absolute edge, not of space itself, but of causality, of what we can ever reach or influence. In 1929, Edwin Hubble made a discovery that would transform our understanding of the cosmos. He'd been measuring the velocities of galaxies using spectroscopy, analyzing how their light was shifted toward the red end of the spectrum. Redshift happens when an object moves away from you. It's like the Doppler effect with sound. An ambulance siren drops in pitch as it drives away because the sound waves get stretched. Light waves work the same way. When a galaxy moves away from us, its light gets stretched to longer, redder wavelengths. Hubble found that nearly every galaxy he observed showed redshift. They were all moving away from us. But more remarkably, he discovered a pattern. The farther away a galaxy was, the faster it was receding. Galaxies twice as far away were moving away twice as fast. Galaxies 3 times as far were moving 3 times as fast. Distance and recession velocity were proportional. This relationship is now called Hubble's law. At first glance, this seems to suggest we're at the center of some cosmic explosion with everything fleeing from us. But that's not what's happening. Imagine a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. From any raisin's perspective, all the other raisins appear to be moving away, with more distant raisins moving faster. But no raisin is at the center. The dough itself is expanding, carrying the raisins along with it. The universe works the same way. Galaxies aren't flying through space away from us. Space itself is expanding, carrying galaxies along with it. Every galaxy sees every other galaxy moving away, with the relationship between distance and velocity being the same from every vantage point. This is crucial. Galaxies aren't moving through space faster than light. That would violate special relativity. Instead, space between galaxies is stretching. The galaxies are relatively motionless within their local patches of space, but those patches are moving apart as new space is created between them. Think of dots drawn on a balloon. As you inflate the balloon, the dots move apart, not because they're sliding across the rubber, but because the rubber itself is stretching. The dots aren't moving through the rubber, they're being carried by the rubber. This expansion isn't happening within space. It's an expansion of space itself. And here's where things get strange. Because the expansion is a property of space rather than motion through space, it's not limited by the speed of light. Objects can't move through space faster than light. That's a fundamental law of physics. But space itself can expand at any rate. And for sufficiently distant objects, the expansion of space between us and them can exceed the speed of light. The Hubble constant, the rate of expansion, is currently measured at about 70 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, the recession velocity increases by 70 kilometers per second. Do the math. At a distance of about 14 billion light-years, the recession velocity reaches the speed of light. At greater distances, space is expanding so fast that the recession velocity exceeds light speed. This doesn't violate relativity because nothing is moving through space faster than light. The space between us and those distant regions is simply expanding faster than light can traverse it. Let's be very clear about what's happening here because it's deeply counterintuitive. Special relativity tells us that nothing can move through space faster than light. If you're in a spaceship and you fire your engines, you can approach the speed of light, but you can never quite reach it, let alone exceed it. The laws of physics absolutely forbid it. But general relativity, Einstein's theory of gravity and space-time, allows space itself to expand at any rate. There's no speed limit on the expansion of space. Imagine you're an ant trying to walk across a rubber band toward a piece of food at the other end. You can walk at, let's say, 1 inch per second. But someone is stretching the rubber band. If they stretch it slowly, say, 0.5 inch per second, you can make progress. You're walking forward at 1 inch per second while the rubber stretches at 0.5 inch per second, so you have a net progress of 0.5 inch per second toward the food. But if they stretch the rubber band faster than you can walk, say 2 inches per second, you make no progress at all. You're walking forward at 1 inch per second, but the rubber is stretching at 2 inches per second, so you're actually moving backward relative to the food, even though you're walking forward as fast as you can. Now, imagine the person stretching the rubber band speeds up over time. Even if you were initially making progress, eventually the stretching becomes so fast that you start losing ground. The food gets farther away, not closer, even though you never stop walking toward it. This is exactly what's happening with distant galaxies. Light from those galaxies is traveling toward us at light speed, the fastest possible speed. But the space between us and them is expanding faster than light can cross it. The light is making no progress. In fact, the galaxy is getting farther away from us over time, even though the light is traveling toward us at maximum speed. There's a distance beyond which this happens, a boundary beyond which galaxies are receding from us faster than light. This distance is currently about 14.4 billion light-years, a boundary called the Hubble sphere. Galaxies beyond the Hubble sphere are receding faster than light. Light they emit toward us is making no progress, or even losing ground, getting farther from us rather than closer. But here's where it gets even stranger. We can still see galaxies beyond the Hubble sphere. In fact, we can see galaxies up to about 46 billion light-years away. How is this possible if those galaxies are receding faster than light? Because they weren't always beyond the Hubble sphere. When the light we're seeing now was emitted billions of years ago, those galaxies were closer. within the Hubble sphere, and their light could make progress toward us. Over billions of years as that light traveled, the expansion of space carried the source galaxy beyond the Hubble sphere. But the light that was already en route continued its journey and eventually reached us. We're seeing these galaxies as they were in the distant past, when they were close enough that their light could reach us. But the light they're emitting right now will never reach us. Those photons are being emitted into space that's expanding away from us faster than light can traverse it. They're losing ground, getting farther from us with every passing moment, and will continue moving away forever. This creates a profound boundary, not in space but in causality. There are galaxies we can see but can never reach. There are galaxies we can see now but whose current state we'll never observe. And there are galaxies beyond our view that we'll never see at all, no matter how long we wait. This boundary is called the cosmic event horizon. It's currently at about 16 billion light-years away, though the exact distance depends on dark energy's properties and how the expansion rate changes over time. Galaxies beyond the cosmic event horizon are causally disconnected from us. Light they emit today will never reach us. Signals we send toward them will never arrive. We cannot affect them. They cannot affect us. For all practical purposes, they exist in a separate universe, a region of space that will never be part of our future light cone. And here's what makes this truly permanent. The cosmic event horizon isn't static. It's not a fixed distance we could eventually reach if we had enough time. As the universe expands and expansion accelerates due to dark energy, the cosmic event horizon actually gets closer to us over time. Galaxies that are currently just within our reach, just barely within the cosmic event horizon, will cross it in the future. They'll slip beyond our ability to ever contact them. We'll still see them for billions of years. The light they emitted in the past will continue arriving, but that light will grow increasingly redshifted, dimmer, stretched out over longer and longer wavelengths. Eventually, the last photon from each of these galaxies will arrive. After that, silence. They'll fade from view, not because they've been destroyed, but because their light can no longer reach us. They'll still exist, still contain billions of stars, still host countless worlds. But they'll be forever beyond our horizon, unreachable and unobservable. In the far future, trillions of years from now, the observable universe will be much smaller than it is today. Most of the galaxies we can currently see will have crossed the cosmic event horizon. Future civilizations, if any exist, will look out and see a much lonelier universe. Perhaps just their own galaxy, perhaps a few others in their local gravitationally bound cluster. Everything else will have vanished beyond the horizon. This is a true edge, not an edge in space, but an edge of causality. There are regions of space we can never reach, never observe, never influence, no matter how long we wait or how fast we travel. The expansion of space creates a permanent isolation, dividing the universe into causally disconnected regions. You can travel toward those distant galaxies at nearly the speed of light, but you'll never catch them. They're receding faster than you can approach. It's like running on a treadmill that speeds up faster than you can run. You're moving forward as fast as physically possible, but you're losing ground. The universe has an edge, not an edge in space, but an edge in time and causality. A horizon beyond which we cannot pass. We've established that there's a cosmic horizon beyond which we cannot see or reach. But what lies beyond that boundary? If the universe is infinite, as the evidence suggests, then beyond our observable sphere, stretches more space, more galaxies, more structure extending forever. And if space truly goes on infinitely, something remarkable and unsettling follows. There must be infinite copies of you out there. Not similar people, exact duplicates living identical lives, making identical choices, reading these exact words at this exact moment. This isn't science fiction. It's a mathematical consequence of infinity combined with the laws of probability. Before we explore the implications of an infinite universe, we need to understand what infinity actually means. Because infinity isn't just a very large number. It's a completely different category of quantity, one that behaves in ways that violate our everyday intuitions. The most famous illustration of infinity's strangeness is the Infinite Hotel, a thought experiment proposed by mathematician David Hilbert. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, and so on forever. Every room is occupied. A new guest arrives and asks for a room. In a normal hotel, you'd say, "Sorry, we're full." But in the Infinite Hotel, the manager says, "No problem," and asks every current guest to move to the next room number. Guest in room 1 moves to room 2. Guest in room 2 moves to room 3, and so on. This frees up room 1 for the new guest. Now imagine infinitely many new guests arrive, each needing a room. Can you accommodate them? Yes. Ask every current guest to move to twice their current room number. Guest in room 1 moves to room 2. Guest in room 2 moves to room 4. Guest in room 3 moves to room 6. This frees up all the odd-numbered rooms, an infinite set for the new guests. You've added infinite guests to infinite guests, and you still have room. Infinity plus infinity equals infinity. This violates everything we know about addition, but it's mathematically rigorous. It's how infinity actually works. Here's another strange property. Some infinities are bigger than others. The set of whole numbers, 1, 2, 3, 4, and so on, is infinite. The set of real numbers, including all decimals and fractions, is also infinite. But mathematician Georg Cantor proved in the 1870s that the real numbers are uncountably infinite, a strictly larger infinity than the countable infinity of whole numbers. You cannot make a list that includes every real number, no matter how you try. There will always be real numbers missing from your list. The real numbers are more infinite than the whole numbers, in a precise mathematical sense. This has implications for an infinite universe. If space is continuous and infinite, it contains uncountably many points. If space is quantized at the Planck scale, the smallest meaningful distance, about 10 to the 35 meters, and infinite, it contains countably many regions. The type of infinity matters. But regardless of which type applies, infinity has a crucial property for our purposes. In an infinite set with finite possibilities, every possibility occurs infinitely many times. Think about flipping a coin. Each flip has 2 possible outcomes, heads or tails. If you flip it 10 times, you might get 7 heads and 3 tails, or any other combination. But if you flip it infinitely many times, every possible finite sequence will occur infinitely often. The sequence heads, heads, tails will appear infinitely many times. So will heads, tails, heads. So will any other sequence you can imagine. This principle extends to more complex situations. If you have a finite number of possible configurations and you sample infinitely many times, every configuration must appear infinitely often. And this brings us to the uncomfortable implication. If the universe is infinite and matter is distributed roughly uniformly, then every possible arrangement of matter must occur somewhere, including arrangements identical to you. Consider a region of space the size of the observable universe, about 93 billion light-years across. Within that volume, there are roughly 10 to the power 80 particles. That's a 1 followed by 80 zeros. These particles can be arranged in different ways, different positions, different velocities, different quantum states. How many possible arrangements are there? The number is incomprehensibly large, but it's finite. Some calculations suggest around 20 different possible configurations, a number so large that writing it out would require more atoms than exist in the observable universe. But it's still finite. There are that many possibilities, and no more. Each possible arrangement corresponds to a different way the particles could be distributed within that volume. Now, if the universe is infinite, there are infinitely many such volumes. Infinitely many 93 billion light-year spheres scattered across space. Here's the unavoidable conclusion. If there are infinitely many volumes but only finitely many possible configurations, then every configuration must repeat. It's not just likely, it's mathematically certain. This means there are infinitely many regions exactly identical to our observable universe. Not similar, identical down to every atom, every arrangement, every quantum state. Every possible configuration occurs somewhere and occurs infinitely many times. Right now, in some region of space incredibly far beyond our cosmic horizon, there's another Earth. On that Earth is another you, living in another copy of your house, reading these exact words at this exact moment. Your thoughts are identical. Your memories are identical. Your future will unfold identically. At least until random quantum events cause your paths to diverge. And there aren't just one or two copies. There are infinitely many. Infinitely many versions of you, all existing simultaneously in different parts of infinite space. This isn't speculation. It's not a fantasy. It's a direct mathematical consequence of two premises. The universe is infinite, and it's roughly uniform on large scales. If both premises are true, and current evidence suggests they are, then infinite duplicates are inevitable. There are also infinitely many regions that are almost identical to ours, but with small differences. A version of you who chose coffee instead of tea this morning. A version who took a different job. A version who was never born. Every possible variation, every possible history exists somewhere. If this seems absurd, remember, infinity is large enough to contain everything. Not just everything that happened, but everything that could have happened. All possible arrangements, all possible histories, all playing out in different cosmic neighborhoods across infinite space. These duplicate regions are beyond our cosmic horizon. We can never see them, never reach them, never communicate with them. They might as well be in separate universes. But if the universe is truly infinite, they exist. Physicist Max Tegmark has calculated how far away your nearest duplicate is likely to be. The distance is incomprehensibly vast, roughly 10^10^29 meters. That's not 10 billion light years or 10 trillion light years. It's 10 to the power of 10 to the power of 29. A number so large it's almost meaningless. But in an infinite universe, that nearest duplicate exists. And beyond that duplicate are infinitely many more, scattered through endless space like variations on a theme, each living their own version of a life that, in some cases, is identical to yours, down to the last detail. This concept of infinite duplicates across infinite space is sometimes called the quilted multiverse, or the level Y multiverse in cosmological taxonomy. It's the simplest type of multiverse. It doesn't require any exotic physics or speculative theories. It emerges naturally from the combination of spatial infinity and the finite number of ways particles can be arranged. Think of it as a vast quilt, with each patch representing an observable universe-sized region. Each patch has its own configuration of matter, its own galaxies, its own history. Most patches are different from ours, different arrangements, different outcomes. But with infinitely many patches, every possible configuration appears infinitely many times. From our perspective, each of these patches might as well be a separate universe. They're beyond our cosmic horizon, causally disconnected from us. We can never observe them, never visit them, never interact with them. The expansion of space ensures permanent isolation, but they're not separate universes in the traditional sense. They're all part of the same continuous space, the same physical reality, governed by the same laws of physics. They're just distant neighborhoods in an infinite cosmos. This quilted multiverse is distinct from other multiverse concepts we'll discuss later. It doesn't involve parallel quantum branches or separate bubble universes or alternate dimensions. It's simply the recognition that if space goes on forever, with matter distributed throughout, then every possible arrangement must occur somewhere. The philosophical implications are profound. It means that somewhere, incredibly far away, there are civilizations identical to ours, making the same discoveries, asking the same questions, arriving at the same answers. There are versions of Earth where history unfolded differently, where Rome never fell, where Columbus never sailed, where you made different choices at crucial moments. All of this exists not in some imaginary parallel world, but in actual physical space, in regions we simply cannot access due to the cosmic horizon. Some philosophers find this unsettling. It seems to rob our choices of meaning. If every possible outcome happens somewhere, why does it matter what we choose? But this is a misunderstanding. Your choices still determine which outcome occurs here in this region of space. The existence of other regions where different choices were made doesn't diminish the reality or importance of your actual choices in your actual location. Others find it comforting. In an infinite universe, everything that can happen does happen somewhere. Every possibility is realized. The full potential of reality is expressed across infinite space. Either way, if the universe is truly infinite and roughly uniform, the quilted multiverse is real. Beyond our cosmic horizon stretch infinite regions, infinite variations, infinite duplicates. Not in some speculative parallel dimension, but in actual physical space, just very, very far away. We've discussed spatial infinity, but there are other types of multiverses proposed by physics based on different mechanisms, and these suggest that beyond our universe might lie not just more space, but entirely different universes with different laws of physics. We've explored the infinite expanse of space, the quilted multiverse of duplicate regions stretching beyond our horizon. But there's another kind of multiverse suggested by modern cosmology, one where our entire universe, with all its observable and unobservable regions, might be just one bubble in an infinite cosmic foam. This isn't the multiverse of science fiction with parallel Earths where history took different turns. This is something stranger. Separate universes that might have completely different laws of physics, different fundamental constants, even different numbers of dimensions. To understand this bubble multiverse, we need to revisit the Big Bang, or more precisely, what happened in the first fraction of a second after it. In the 1980s, physicist Alan Guth proposed a solution to several puzzles about the early universe. He suggested that a tiny fraction of a second after the Big Bang, between about 10^36 and 10^32 seconds, the universe underwent a period of exponential expansion far faster than the normal expansion we see today. During this inflationary period, space doubled in size repeatedly. every minuscule instant. The total expansion was enormous, at least a factor of 10 to 26, possibly much more. An atom-sized region inflated to something larger than the observable universe in less than a trillionth of a second. This solves several problems. It explains why the universe is so uniform. Different regions we see today were once close enough to reach thermal equilibrium before inflation separated them. It explains why space is so flat. Any initial curvature was stretched out, like inflating a balloon until its surface appears flat. But here's where it gets interesting. In the simplest models of inflation, it doesn't end everywhere at once. Imagine inflation as a field filling space, like water filling a pool. In some regions, this field decays and inflation stops, creating a bubble of normal space. A universe like ours where normal expansion takes over and galaxies eventually form. But outside that bubble, inflation continues. Eventually, more bubbles form where inflation stops in other regions. Each bubble becomes its own universe with its own post-inflation evolution, its own Big Bang, its own galaxies and stars. But the space between bubbles continues inflating forever, expanding exponentially, constantly creating more volume. And in that eternally inflating space, more bubbles constantly form. This is called eternal inflation. Once inflation starts, it never completely stops. It ends in localized regions, creating bubble universes, but always continues in the space between bubbles, which expands so fast that new bubbles can form forever. Our universe would be just one bubble in an infinite foam of bubble universes, each forming, expanding, and perhaps eventually dying, while the eternally inflating background continues to expand and spawn new bubbles forever. Each bubble is causally disconnected from the others. The space between them is expanding faster than light, creating permanent isolation. We can never observe other bubbles. We can never receive signals from them. For all practical purposes, each bubble is its own separate universe. But here's what makes this truly profound. Different bubbles might have different physical laws. String theory, one of the leading candidates for a theory of everything that would unify quantum mechanics and gravity, suggests that our universe has more than the 3 spatial dimensions we experience. The theory requires 10 or 11 total dimensions, the 3 we know: length, width, height, plus time, plus 6 or 7 additional spatial dimensions that are curled up extremely small. So small, we don't notice them in everyday life. These extra dimensions must be compactified, folded up into tiny shapes at every point in space. And here's the crucial detail. There are many different ways to compactify these dimensions. Different shapes, different sizes, different topologies. Each different compactification produces different low-energy physics. The masses of particles, the strengths of forces, even which particles and forces exist at all of this depends on how the extra dimensions are curled up. Calculations suggest there might be around 500 different possible compactifications. That's a 1 followed by 500 zeros, vastly more than the number of atoms in the observable universe. This vast collection of possibilities is called the string theory landscape. Each point on the landscape represents a different vacuum state, a different configuration of the extra dimensions, and therefore a different set of physical laws. In our universe, electrons have a certain mass, quarks have certain masses, electromagnetism has a certain strength, and so on. These are the laws we observe, the constants we measure. But they're not necessarily the only possibilities. They might just be the values that happen to exist in our particular vacuum state. Other points on the landscape would have different values, different particle masses, different force strengths, perhaps different numbers of particle types. The laws of physics as we know them might be local, specific to our region of the landscape. If eternal inflation is correct, different bubble universes might settle into different vacuum states. One bubble might have our laws of physics. Another might have completely different laws, perhaps with electrons 10 times heavier, or with gravity 1,000,000 times stronger, or with entirely different particles and forces. Most of these bubble universes would be sterile, unable to support complex structures. If gravity were much stronger, stars would burn out in seconds. If the electromagnetic force were different, atoms might not form. Most of the landscape consists of parameter values hostile to any kind of complexity, let alone life. But in an infinite multiverse where all possibilities are realized, some bubbles would have life-permitting physics. And we necessarily find ourselves in one of those rare bubbles because we couldn't exist anywhere else. This brings us to one of the most controversial ideas in modern cosmology, the anthropic principle. The anthropic principle, in its simplest form, states, we observe the universe to have properties compatible with our existence because if it didn't have those properties, we wouldn't be here to observe it. This sounds tautological, circular reasoning that explains nothing. But in the context of a multiverse, it gains explanatory power. Consider the strength of gravity. If gravity were just slightly stronger, stars would burn their fuel too quickly. The sun would exhaust itself in millions rather than billions of years, not leaving enough time for complex life to evolve. If gravity were slightly weaker, stars might never ignite at all, or they'd burn so slowly and dimly that planets would freeze. The actual strength of gravity falls within a narrow, life-permitting range. Why? In a single universe, this seems like an extraordinary coincidence. The odds of randomly getting a life-permitting value seem vanishingly small. Some see this as evidence of design. The universe appears fine-tuned for life. But in a multiverse with 10 to 500 different bubble universes, each with different physical constants, it's not a coincidence at all. Most bubbles have the wrong values and remain sterile, but some, by pure chance, have values that permit stars, planets, chemistry, and eventually life. We necessarily find ourselves in one of the rare life-permitting bubbles, not because the multiverse was designed for us, but because we couldn't exist in any of the sterile bubbles. Our existence acts as a selection effect, determining which type of bubble universe we can observe. This explains apparent fine-tuning without invoking design. The universe seems fine-tuned for life because we're observing a sample biased by our own existence. We can only observe universes where observers can exist. Some physicists find this deeply unsatisfying. It seems to give up on finding deeper explanations, settling for, it's this way because it has to be this way for us to exist. Others argue it's the only explanation that makes sense given the multiverse landscape. Either way, if eternal inflation and the string landscape are correct, our universe is just one pocket among infinitely many, each with its own laws, its own history, its own possibility for structure and complexity. Most are dead. We inhabit one of the rare exceptions, not because we're special, but because the alternatives couldn't produce observers. The multiverse, if real, is mostly empty, mostly sterile, mostly dark. We exist in a rare oasis of life-permitting physics. We've explored edges in space, the cosmic horizon, the boundaries created by expansion, the separation between bubble universes. But the universe also has edges in time. A beginning, approximately 13.8 billion years ago, and an ending, trillions upon trillions of years in the future. These temporal boundaries are as real as any spatial edge, perhaps more so. They represent moments when the very nature of reality changes, when the rules break down, when time itself becomes meaningless. Let's journey to both edges of time, to the moment when everything began, and to the distant future when everything ends. Run the expansion of the universe backward. Galaxies converge, space contracts. The universe becomes denser, hotter. Continue rewinding and everything, all matter, all energy, all space itself, converges toward a single point. This is the Big Bang singularity, the moment when the universe began. At the singularity, density becomes infinite. Temperature becomes infinite. The curvature of space-time becomes infinite. The equations of general relativity break down completely. They can't describe what happens at this point because they produce nonsensical results, infinities that can't be interpreted physically. This singularity represents a genuine edge in time. Before this moment, there was no before. Time itself didn't exist. Space didn't exist. The universe didn't exist as empty void waiting to be filled. There was no universe at all. This is profoundly difficult to grasp. We're used to thinking of time as a line extending forever in both directions. Every moment has a previous moment. Every event has a cause that preceded it. But the Big Bang breaks this pattern. At the singularity, time begins. There is no earlier time. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question itself doesn't make sense because before requires time, and time starts at the Big Bang. Some physicists suggest the singularity might not be truly infinite. Quantum effects, which general relativity doesn't account for, might prevent densities from becoming infinite. Instead of a point of infinite compression, the universe might have bounced from a previous contracting phase or emerged from some quantum foam of fluctuating space-time. Loop quantum gravity, one approach to quantum gravity, suggests the Big Bang was actually a big bounce. The universe contracted to an extremely small but finite size, then bounced back into expansion. In this picture, there was a before, a previous universe that collapsed and rebounded into our current expanding phase. String theory offers other possibilities. Perhaps our universe emerged as a bubble from a higher dimensional space. Perhaps it nucleated from quantum fluctuations in some pre-existing framework. But these scenarios just push the question back. If our universe bounced from a previous one, where did that previous universe come from? If it emerged from quantum fluctuations, what determined the rules governing those fluctuations? At some point, you encounter a true beginning, or you accept that the universe has existed eternally in some form. The philosophical and theological implications are obvious. If the universe had a beginning, what caused it to begin? Can something come from nothing? Or must there be an eternal framework, whether God or quantum fields or mathematical necessity, that gives rise to universes? Science can't answer these ultimate questions. We can trace the universe back to the earliest moments we can describe with our theories, perhaps to 10 to 43 seconds after the Big Bang, the Planck time, when quantum gravitational effects become dominant. Before that, our physics breaks down. We enter a realm where we have theories but no experimental guidance, speculation but no certainty. What we can say is this: 13.8 billion years ago, the universe as we know it began. Whether this represents an absolute beginning or a transition from some previous state, we don't know. But for all practical purposes, for everything we can observe and measure, time has a starting point. The universe has an edge in the past, and it will have an edge in the future, though that edge is very different in character. Fast forward from the Big Bang. The universe expands, cools, galaxies form, stars ignite, planets coalesce. Life emerges, at least on one small world, orbiting an ordinary star. This is the era we inhabit, the stelliferous era, the age of stars. It's a brief, bright moment in cosmic history. Stars have been shining for about 13 billion years. They'll continue for perhaps another 100 trillion years before the last one flickers out. After that, the universe enters the degenerate era. No new stars form because all the gas has been consumed or dispersed. The sky goes dark. Only stellar remnants remain. White dwarfs, neutron stars, black holes, slowly cooling toward the temperature of the expanding space around them. This era lasts for perhaps 10 to 40 years, a 1 followed by 40 zeros. During this time, if protons are unstable, and some theories suggest they are, matter itself begins to decay. Planets, asteroids, dead stars, all the solid matter accumulated over trillions of years, slowly disintegrates as protons decay into lighter particles and radiation. By 10 and 40 years, most matter has decayed. What remains are black holes and scattered particles drifting through ever-expanding space. Then comes the black hole era. Black holes dominate the universe. They're the last massive objects, the final remnants of structure. But even black holes don't last forever. In 1974, Stephen Hawking discovered that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly evaporate, losing mass over time. The evaporation is incredibly slow. A solar mass black hole takes about 67 years to evaporate completely. Supermassive black holes take far longer, perhaps 10 to 100 years for the largest ones. These timescales are incomprehensible. A googol is 10 to 100, a 1 followed by 100 zeros. The current age of the universe is only 10 to 10 years. A googol years is so far in the future that the ratio between now and then is vastly larger than the ratio between 1 second and the age of the universe. But given enough time, and the universe has infinite time ahead, even the largest black holes evaporate. Their final moments are dramatic. As a black hole shrinks, its temperature increases. In its last seconds, it flares to incredible brightness, releasing the last of its mass energy in a burst of radiation before vanishing completely. By 10 to 100 years, even the largest black holes have evaporated. Nothing remains but a thin soup of particles and radiation spread across space that's now incomprehensibly vast. The universe has expanded so much that the average density is almost zero, perhaps 1 particle per cubic light year or less. The temperature approaches absolute zero. Energy gradients have been erased. There's no way to extract useful work, no way to power any process. The universe has reached maximum entropy. This is heat death, not an end in the sense that the universe ceases to exist, but an end in the sense that nothing interesting can happen anymore. Time continues, but it's meaningless because nothing changes. The universe has reached equilibrium, a state of perfect disorder from which there's no return. Imagine the universe at 100 years. Space has expanded to such enormous scales that you might travel for billions of light years without encountering a single particle. The temperature is indistinguishable from absolute zero, perhaps 10 to 30 degrees Kelvin. Occasionally, widely separated photons pass each other in the void. Occasionally, an electron drifts through empty space. But these events are rare, separated by vast distances and vast time intervals. Nothing organized exists anymore. No stars, no planets, no black holes, no structures of any kind. Everything has decayed, evaporated, dissipated. The universe is as close to empty as it can be, while still containing anything at all. This is the heat death, predicted by thermodynamics. Every system tends toward maximum entropy, maximum disorder, over time. The universe is no exception. Given enough time, all energy gradients are eliminated, all structure dissolves, all complexity vanishes. From our current perspective, with stars still shining and galaxies still forming and life still evolving, this future seems impossibly bleak. But it's the inevitable consequence of the second law of thermodynamics, combined with the expansion of space. Some physicists have speculated about what might happen after heat death. In a universe with infinite time, quantum fluctuations might eventually, after timescales of 1056 years or longer, create small regions of low entropy through pure chance. These fluctuations might even create brief moments where structure spontaneously forms, particles clustering together, perhaps even briefly forming something resembling a conscious mind before dissolving back into randomness. These are called Boltzmann brains, random fluctuations that briefly mimic conscious experience. In an infinite future, Boltzmann brains would occur infinitely often. This leads to strange philosophical puzzles. In such a universe, most conscious experiences would be brief, random fluctuations rather than genuine, evolved beings. How do we know we're not Boltzmann brains ourselves? Most physicists consider this scenario unlikely or unphysical, but it illustrates the strangeness of thinking about infinite time. Another possibility, the universe might not remain in heat death forever. The cosmological constant, dark energy, might not be truly constant. If it decays over enormous timescales, the universe's expansion might eventually slow or even reverse, leading to a big crunch rather than eternal expansion. Or the universe might undergo vacuum decay, a topic we'll explore shortly, where the current state of empty space transitions to a lower energy state, releasing energy that could potentially create new structure. But based on our current understanding, the most likely fate is eternal expansion toward perfect cold and darkness. The universe will continue existing forever, but in a state where nothing happens, nothing changes, nothing matters. Time, in a sense, ends, not because time itself ceases, but because time becomes meaningless. When nothing changes, when there are no events, no processes, no differences between one moment and the next, what does it mean to say time is passing? This is the ultimate edge of the universe in time. Not a moment when time stops, but a future so entropic that time loses its meaning. The universe reaches a final state from which there is no return. We've explored the edges defined by physics, the cosmic horizon, the temporal boundaries of the Big Bang and heat death, the separation between bubble universes. But there are other possible boundaries, more speculative, more unsettling. Edges that question the very nature of reality itself. What if the universe isn't fundamental? What if it's software running on some computational substrate? What if the vacuum of space is unstable and could suddenly transition to a lower energy state, rewriting the laws of physics in an expanding bubble traveling at the speed of light? These aren't just philosophical thought experiments. They're serious proposals that emerge from physics and information theory, possibilities we can't rule out with current knowledge. In 2003, philosopher Nick Bostrom published a paper outlining what's now called the simulation argument. His reasoning goes like this. Assume three things are possible. First, civilizations can survive long enough to develop powerful computers. Second, these advanced civilizations have reasons to run simulations of conscious beings, perhaps for research, entertainment, or historical reconstruction. Third, they have enough computing power to run many such simulations. If all three are true, then the number of simulated conscious beings vastly outnumbers real, biological beings. For every real person, there might be thousands or millions of simulated people living in simulated worlds, unaware they're software. By simple statistics, you're more likely to be one of the simulated beings than one of the rare real ones. Most conscious experiences would occur in simulations, not in the base reality. This is disturbing. If the argument is sound, we might be living in a simulation right now. Patterns of information being processed by some computer in another reality. What would this mean for the edge of the universe? Perhaps the universe doesn't extend infinitely. Perhaps it extends only as far as the simulation renders. Regions we haven't observed yet might not exist as detailed simulations. They might be generated only when observed, like a video game that only loads nearby terrain to save processing power. The edge of the universe might literally be the edge of the simulation, the boundary of what's been computed. Beyond that boundary, there might be placeholder code, simplified approximations, or nothing at all, until an observer approaches and forces the simulation to generate more detail. Some have looked for evidence of a simulation. Perhaps there are glitches, anomalies in physics that shouldn't exist. Perhaps the universe has an underlying grid structure, a pixelation at the Planck scale where space-time becomes discrete rather than continuous. Perhaps the speed of light represents a processing speed limit, the maximum rate at which information can propagate through the computational substrate. So far, no convincing evidence has been found. The universe appears continuous down to the smallest scales we can probe. Physics follows smooth differential equations, not the discrete updates of a computer program. The constants of nature appear precisely defined, not like rounded approximations you'd expect from floating-point arithmetic. But absence of evidence isn't evidence of absence. A sufficiently advanced civilization could create simulations indistinguishable from physical reality. If the simulation is good enough, we might never detect it. And here's a deeper problem. Even if we found evidence suggesting we're in a simulation, how would we know it's genuine evidence rather than part of the simulation itself? The simulation could include false clues, red herrings, or programmed glitches designed to mislead us. Any evidence we find could be simulated evidence. The simulation hypothesis is effectively unfalsifiable. We can't prove we're in a simulation, and we can't prove we're not. It exists outside the domain of science because it makes no testable predictions that couldn't be explained by the hypothesis being false. But it represents a type of boundary, not in space or time, but in the substrate of reality itself. If we're in a simulation, the true universe is whatever reality contains the computer running our simulation. Our universe would have an edge at the computational limits of that system. Here's a nightmare scenario that emerges from quantum field theory. What if the vacuum of space, the empty space between particles, isn't in its lowest possible energy state? What if it's in a false vacuum, a metastable state that appears stable but could suddenly decay to a true vacuum with lower energy? In quantum field theory, fields permeate all of space. What we call empty space is actually filled with quantum fields at their ground state. But ground state might not mean the absolute lowest energy state. It might be a local minimum, a valley in the energy landscape that's stable for now, but not the deepest valley possible. Imagine a ball sitting in a shallow valley on a hillside. There's a deeper valley farther down the hill. The ball is stable in its current position. It would take energy to push it out. But if something gives it enough energy to roll over the lip of its current valley, it would roll down to the deeper valley, releasing energy as it goes. The same could happen with quantum fields. If our vacuum is a false vacuum, it could spontaneously tunnel through to a lower energy state, a quantum fluctuation that creates a tiny bubble of true vacuum somewhere in space. Here's where it becomes catastrophic. Once that bubble forms, it expands. The true vacuum has lower energy, so the conversion releases energy. The bubble wall expands at the speed of light, converting false vacuum to true vacuum as it goes, releasing more energy that drives further expansion. Inside the bubble, physics is different. The true vacuum has different field values, which means different particle masses, different force strengths, different physical laws. Atoms might not be stable. Protons might decay instantly. Chemistry as we know it might be impossible. From the outside, you'd see nothing until the bubble wall reached you. It travels at light speed, so there's no warning. One instant, everything is normal. The next instant, the wall hits and the laws of physics change. Everything you're made of disintegrates or transforms according to the new physics. This sounds like science fiction, but it's a real possibility in quantum field theory. Calculations based on the measured mass of the Higgs boson suggest our vacuum might be metastable, stable for now, but not forever. The good news, the decay rate appears to be extremely low. The estimated lifetime before vacuum decay might be 100 years or longer, far longer than the current age of the universe, far longer even than the heat-death timescale. We're probably safe, but probably isn't certainly. A vacuum decay bubble could form somewhere in the universe, tomorrow, expanding at light speed, eventually reaching Earth and rewriting the laws of physics here. We'd never see it coming. This represents another type of edge, not a fixed boundary in space, but a potential boundary that could form anywhere, anytime, expanding outward at maximum speed. Inside the bubble, one universe. Outside, another. The boundary between them is a phase transition, a place where the fundamental nature of reality shifts. If vacuum decay is possible and has happened elsewhere in the universe, there might be expanding bubbles of altered physics out there right now, beyond our horizon, rewriting reality as they grow. There's one more speculative boundary worth mentioning. The boundary of what the universe allows, enforced not by lack of space or time, but by the laws of physics themselves. Stephen Hawking proposed the chronology protection conjecture in the early 1990s. The idea is that the laws of physics might conspire to prevent certain kinds of boundaries, specifically boundaries in causality like closed time-like curves that would allow time travel to the past. General relativity permits solutions where space-time curves so extremely that paths through it loop back in time. These are called closed time-like curves. If you followed one, you'd travel into your own past, potentially creating paradoxes, killing your grandfather before your parent was born, preventing your own existence. Hawking suggested that whenever space-time begins to curve toward forming such a loop, quantum effects would intervene. Vacuum fluctuations would become infinite, creating a firewall of energy that destroys anything trying to use the closed time-like curve. The universe, in effect, protects chronology by making time machines impossible. This isn't proven, but it suggests an interesting principle. Maybe the universe has built-in protections, boundaries enforced by physics itself, that prevent us from reaching certain edges even if we had the technology to try. We can't travel faster than light, not because we haven't built a fast enough engine, but because the universe forbids it. Perhaps we can't time travel, can't access certain regions of space-time, can't probe certain scales, not because of technological limitations, but because physics itself creates impassable boundaries. These boundaries wouldn't be walls in space. They'd be limits encoded in the structure of reality itself. Forbidden zones not because nothing exists there, but because the laws of nature prevent access. There might be regions of space-time, perhaps near black hole singularities, or in the first moments after the Big Bang, or in the final instance of vacuum decay, that are fundamentally inaccessible, protected by physics from any possible observation or interference. Roger Penrose has speculated about cosmic censorship, The idea that singularities are always hidden behind event horizons, never naked and visible. Perhaps this is another form of chronology protection, the universe hiding its most extreme boundaries behind impassable barriers. If such protections exist, they represent a profound type of edge, not a place where the universe ends, but a place where the universe prevents you from going. Not absence, but prohibition. The edge exists not in space or time, but in what's permitted by the fundamental laws. We don't know if chronology protection is real. We don't know if there are other similar principles that create inaccessible regions. But the possibility suggests that some boundaries might be written into the fabric of reality itself. Edges defined not by where things are, but by what nature allows. These speculative boundaries, simulation limits, vacuum decay, chronology protection, might seem far-fetched, but they emerge from serious physics and philosophy, reminding us that the edges of reality might be stranger than we imagine. We began this journey by asking a simple question: where does the universe end? We've traveled from ancient domes to cosmic horizons, from the mathematics of infinity to the physics of vacuum decay, from the first moment of time to the final fade into darkness, trillions of years hence. And now, at the end of our exploration, we can finally offer an answer, or rather several answers, because the question has many layers, and each layer reveals a different kind of boundary. The universe has edges, but not the kind ancient peoples imagined. There's no cosmic wall, no firmament, no place where space simply stops. Instead, we've discovered multiple boundaries, each representing a different limitation on what we can observe, reach, or influence. There's the observable universe, the sphere extending 46.5 billion light-years in every direction. This isn't an edge in the universe itself, but an edge in our perception, defined by how far light has had time to travel. Beyond this horizon lies more universe. Probably much more, possibly infinitely more. There's the cosmic event horizon, the boundary beyond which galaxies are receding faster than light. This represents a true edge in causality. Regions beyond this horizon are forever unreachable, no matter how fast we travel or how long we wait. The expansion of space creates permanent isolation. There's the geometry of space itself. Current measurements suggest the universe is flat, which implies it's likely infinite, extending forever with no spatial boundary at all. If space goes on infinitely, then everything that can happen does happen somewhere, including infinite copies of you in regions far beyond our horizon. There are the bubble universes of eternal inflation, separate pocket universes with potentially different laws of physics, separated from us by eternally expanding space. These represent boundaries between different physical realities. There are the temporal boundaries, the Big Bang singularity, 13.8 billion years ago where time began, and the heat death trillions of years in the future where time becomes meaningless because nothing changes anymore. And finally, there are the speculative boundaries, simulation limits, vacuum decay bubbles, chronology protection, edges that might exist as limits encoded in the laws of nature themselves. So where does the universe end? If you mean where does space stop, the answer is probably nowhere. Space likely extends infinitely, or at least far beyond what we can observe. If you mean what can we observe, the answer is clear. About 46 billion light-years in every direction, and no farther. If you mean what can we reach, the answer is sobering. Only a small fraction of the observable universe before accelerating expansion carries distant regions permanently beyond our grasp. If you mean when does the universe end, there are two answers. It began 13.8 billion years ago, and it will effectively end when it reaches heat death. Probably more than 100 years from now. We are specks on a speck, living on a small planet in one of hundreds of billions of galaxies, in one observable patch of what might be an infinite cosmos. We exist for a brief moment between the fiery beginning and the frozen ending. But we're also extraordinary specks. We can measure the universe, we can trace its history and predict its future. We can understand our place in this vast reality. So tonight, as you settle into the quiet, let yourself feel both the smallness and the grandness of your existence. You are small. Your entire civilization has existed for perhaps 10,000 years, less than 1/1,000,000th of the universe's age. Your planet is one among trillions. Your observable universe is likely a tiny patch of something vastly larger, possibly infinite. But you are also connected. The atoms in your body were forged in dying stars billions of years ago. The oxygen you breathe was created through stellar fusion. The carbon in your cells was synthesized in stellar cores and scattered by supernovae. You are made of processed stardust, assembled into patterns complex enough to contemplate the cosmos that created you. The boundaries we've explored tonight exist whether you think about them or not. The universe extends far beyond what you can see, probably far beyond what anyone can ever see. Somewhere, incredibly far away, there might be another you, living an identical life, connected to you not by causality, but by the mathematical necessity of infinite space. These ideas should inspire wonder. The universe is so much larger, so much stranger, so much more magnificent than our everyday experience suggests. We live in an age where we can measure these distances, trace these boundaries, understand these cosmic structures. But these ideas should also inspire humility. Most of reality is beyond our reach. Most of cosmic time lies either before our existence or far beyond our extinction. We are temporary patterns in an ancient cosmos, brief expressions of complexity in a universe that trends inexorably toward disorder. This perspective can feel overwhelming, or it can feel liberating. You don't carry cosmic significance on your shoulders. You're allowed to be small. You're allowed to care about small things, your relationships, your daily joys, your immediate concerns. The universe's vastness doesn't diminish the reality of your experience here, now, in this moment. If this journey to the edge of all things has expanded your sense of wonder tonight, a gentle like or subscribe to Space Doze would mean everything to me. It lets me know you're out there listening in the quiet hours, finding peace in these explorations of the vast and the strange. Your presence here matters. Every person who pauses to wonder about the boundaries of reality, to seek understanding of the cosmos, you're part of something important. You're the universe becoming aware of itself, however briefly. Sleep well, Stardust. The edge is far, but the eye spiral holds you close. You're at the center of your own horizon, exactly as everyone else is at the center of theirs. You're home. The cosmos is vast, ancient, and mostly empty. But here, on this small world, in this brief moment, consciousness arose. That's remarkable. That's beautiful. Good night.